Okay, the next practice problem we're going to do for section 12.3 on the dot product is question number 12. It asks us to find the scalar and vector projections of vector A onto vector B. I've added the labels in because they just gave the coordinates, and I think it's easier to actually talk about points or actual vector labels. Okay, in order to find the scalar projection of A onto B, what we're looking for is this. A, B, actually the length, that's always going to be equal to the dot product of A and B divided by the magnitude of B. And that will give me the length of the projection of A onto B. And that's because that's what the dot product does, is it will calculate for me the magnitude of B times A projected onto B's magnitude. Okay, so to do this, we just need in the numerator the dot product, and that's going to be 1 times 1, which is 1, plus 2 times 2, which is 4, and the third component's going to be 0, so it's 4 plus 1, or 5. The denominator then will be the magnitude of B, which is the square root of 5, because it'll be 1 squared plus 4 squared, and that's, or 2 squared, and that's 4 plus 1, which is 5, so the square root of 5. I can simplify that a little bit or rationalize the denominator and just make it radical 5 by multiplying by radical 5 over radical 5. So square root of 5 is the magnitude of the vector projection of A onto B. The next thing we want is the actual value of A sub B as a vector. That is, we want the vector components for it. And in order to do that, we're going to use the same thing, A dot B divided by the size of B, but now we're going to multiply it by a unit vector in B's direction. And of course, to find a unit vector in B's direction, I'm going to need to take the vector B and I'm going to need to divide it by B's magnitude. Well, we've already calculated B's magnitude, it's radical 5, so I'm basically going to divide B by radical 5. B is 1, 2, 0, and we're going to divide that by the square root of 5. So every component will simply be divided by radical 5. That means the x component is 1 over radical 5, the y component is 2 over radical 5, and the z component is still 0. So this is the unit vector in B's direction. It has a magnitude of 1. You can check it with the Pythagorean theorem, but it points in B's direction. So now I can take the square root of 5, which was the magnitude of the projection of A onto B, and multiply it by the unit vector in B's direction, which is 1 over radical 5, 2 over radical 5, and 0. And of course, that will produce the vector 1, 2, 0. So it turns out that that vector B itself was exactly the right size to be the projection of A onto B. And this tells us something unusual, and that is if we project vector A onto B, we're going to end up with a projection that's exactly equal to B itself. And of course, if we look at the components, we can see that. Vector A was 1, 2, 3, and vector B was 1, 2, 0, which means they pointed in the same direction in the x and in the y. It's just that vector A pointed up by 3 and vector B lay in the xy plane. And as a result of that, projecting A onto B just meant reducing it by that 3 in the z direction in order to project it in a perpendicular way onto the vector that was in the xy plane. So it makes perfect sense that in this case, because of these coordinates, that the magnitude of vector projection of A onto B was the same magnitude as vector B, and the actual vector of A projected onto B was identical to vector B.